picture this. You're cruising down the highway in a brand new state-of-the-art electric vehicle.
Yeah, just totally smooth.
Right, exactly. You've got your favorite music playing, the climate controls at like perfect 70 degrees, and the ride is just incredibly smooth.
And quiet. That's the big thing.
Totally quiet. There's practically no engine noise, no rumble of exhaust, no vibration coming through the steering wheel, no dramatic shifting of gears throwing you back and forth.
It's a very serene environment.
It really is. It feels like you're just gliding on a cloud, completely isolated from the mechanics of the outside world. But beneath that silent floorboard,
Oh, yeah.
just a few feet away from where you're resting your shoes, there is this absolute violent multi-physics war raging at tens of thousands of RPMs.
It's wild. The juxtaposition is, it's honestly one of the most fascinating aspects of modern automotive design.
Yeah.
Because the driver experiences this insulated, almost cathedral-like cabin environment. But the mechanical reality inside the vehicle's drive unit is, well, it's closer to the inside of a jet turbine.
Wow, a jet turbine.
Yeah, I mean, the rotational speeds, the thermal loads, the electromagnetic forces at play, they are just staggering.
Because we're used to gas cars, right?
Exactly. We spent a century perfecting the internal combustion engine. And in those, the violence of contained explosions is something you can actually hear and feel.
Right, you feel the engine revving.
But in an EV, that violence is silent. And it's operating on this microscopic, almost quantum level.
And that hidden war is exactly what we're focusing on today for our deep dive. So, okay, let's unpack this.
Let's do it.
We've gotten our hands on this incredibly detailed 80-page forensic engineering manual.
Which is incredibly dense, by the way.
Oh, it's so dense. It translates roughly to E-axle differential bearing failure analysis and prevention strategies.
Which sounds dry, but it is basically a thriller.
It really is. It's this internal, highly technical look into the electric drive axle, the E-axle, and specifically why this tiny little component called a differential bearing is getting absolutely shredded.
Under some very extreme conditions.
Right. So our mission for this deep dive is to decode those invisible forces, destroying these EV components, and, explore how engineers are fighting back.
Building what the document calls a great wall of reliability.
I love that phrase, protecting the entire life cycle of the machine. But, I mean, it's not like fixing a normal car, is it?
Not at all. It is crucial to understand that in the world of EVs, a mechanical failure is, well, it's almost never just a mechanical failure.
What do you mean?
Like in a traditional gas-powered car, if a wheel bearing breaks, a mechanic assumes it was, bad steel. Or maybe dirt got in.
Yeah, just a normal physical problem.
Right. But in an EV, we are dealing with this deeply intertwined collision of thermodynamics, high-voltage electrical chemistry, and just pure physics.
So it's all connected.
Intimately connected. The E-axle isn't just a metal box full of gears. It's a highly integrated electromechanical ecosystem.
Okay.
So when a bearing fails in that ecosystem, the root cause could be buried in the software code or the frequency of the inverter.
Wait, software can break a physical piece of steel?
Oh, absolutely. Or it could be the thermal limits of the cooling jacket.
Yeah.
It is a brilliant, terrifying puzzle.
It really is like a high-stakes detective story. These engineering teams are hunting a killer that leaves almost no trace.
None at all.
So we're going to trace the physics of the failure first.
Yeah.
You know how forces you can't even see rip solid steel apart.
And then the forensic tools they use.
Right, which involves some mind-bending acoustic and electrical diagnostics.
Yeah.
And finally, how they apply emergency triage to fix the cars already on the highway.
Because there are thousands of them out there.
Exactly. So let's start right at the site of the crime. The document focuses on the differential needle bearing.
Yes.
For anyone who hasn't, rebuilt a transmission in their garage, how does a needle bearing differ from a standard ball bearing, like in a skateboard?
Well, a standard ball bearing uses perfectly round steel spheres. They reduce friction, and they're great for high speeds.
Okay, spheres.
But because they're spheres, they only touch the metal tracks around them at a single microscopic point. We call it a point contact.
Makes sense.
A needle bearing, though, doesn't use spheres. It uses tiny solid steel cylinders. Think of miniature rolling pins.
Oh, okay. Mini rolling pins.
Right. And because they are cylinders, they make a line of contact, not a point.
So they're spreading the weight out more?
Massively. It increases the surface area, which allows it to handle vastly higher radial loads.
The heavy downward crushing forces.
Exactly. In a very compact space, which you need in a differential managing massive EV torque.
Right, they had to take a beating.
Yeah.
But the manual notes the main symptom they find in these broken E-axles is something called short edge spalling.
Yes, bullet.
which basically means the metal is flaking off, right? Like chips of steel breaking away from those tiny rolling pins.
That's right. It's a classic form of surface fatigue. Imagine repeatedly driving a fully loaded dump truck over a brittle concrete floor.
Okay.
The floor holds up for the first 100 trips, maybe, but eventually the cyclical stress causes micro cracks below the surface.
And then it just crumbles.
Yeah, the cracks propagate up and chunks of concrete flake away. That's what happens to the crystalline structure of the steel bearing under repetitive pressure.
But the engineers noticed something weird about where the damage was,
Okay.
right?
What's fascinating here is the specific location. It's short edge spalling. It's not happening in the middle of the cylinder where the load should be even.
It's at the tips.
Exclusively at the extreme outer edges of those tiny steel rollers.
And the root cause they found for this edge destruction is called GSC, geometric stress concentration,
Right.
which basically means the physical shape is forcing all the stress into one tiny spot. And the manual gives a threshold for this, which is terrifying.
It really is.
They say an angular misalignment, a microscopic tilt of the bearing of just 1 milliradian, is enough to violently push all the pressure to the ends.
1 milliradian.
I looked this up. It's 1,000th of a radian. In degrees, it's like 0.057 degrees.
It's nothing.
If you held a meter stick perfectly straight, a 1 milliradian tilt means the end of the stick is only 1 millimeter off center. That's practically invisible.
It is invisible to the eye, but you have to contextualize that tilt within the bearing's environment.
Okay, how so?
Between the hard steel bearing and the metal housing, there's a microscopic film of oil. It acts as a hydrodynamic wedge.
Like a liquid cushion.
Exactly. It keeps the microscopic metal peaks from ever actually touching. But when you tilt that solid steel cylinder by just 1 milliradian,
You completely alter the geometry.
you do. You alter the entire load distribution.
It makes me think of like someone trying to balance a heavy refrigerator.
Okay, yeah.
But instead of resting it on 4 wide feet, they balance the entire weight on the tip of a single stiletto heel.
That's a great analogy.
The fridge weighs the same, but because you concentrated all that force onto an area the size of a dime, it punches straight through the linoleum floor.
The linoleum isn't weak. The geometry is just punishing. The total torque from the motor is constant, but the area absorbing it shrinks drastically.
And this caused a huge shift for the engineers, right?
A massive paradigm shift. Allegorically, if you tore down a transmission and saw a flaking bearing, you just assumed it was a metallurgical defect.
Bad steel.
Yeah, you'd call the supplier, demand to know why you got bad steel, or assume the heat treating was flawed.
But it wasn't the steel.
No, the forensic analysis proved the steel was flawless. The failure is entirely geometric and systemic.
Or was it that tilt?
Right. When that 1 milliradian tilt happens, the contact stress at the edge skyrockets. The document notes it exceeds 2.5 gigapascals.
Okay, 2.5 gigapascals. Let's put that into perspective for a second.
It's a lot.
Atmospheric pressure, the air pushing down on us right now, is about 100 kilopascals. The pressure at the very bottom of the Mariana Trench is roughly 100 megapascals.
Right.
2.5 gigapascals is 25 times the crushing pressure at the bottom of the ocean, focused onto a sliver of steel the width of a human hair.
It's an astronomical amount of force. It far exceeds the yield strength of even the most advanced bearing steel.
It just obliterates the oil film.
Instantly. The metal-to-metal contact is so severe, the crystalline lattice of the steel simply yields. It fractures.
Creating the spalling.
Yes. And then it's a death spiral. Jagged debris gets carried by the oil through the axle, acting like liquid sandpaper.
Destroying the whole unit.
Exactly.
Okay, so if the steel is strong, and it requires this tiny 1 milliradian tilt to trigger the pressure spike, what massive force is shoving solid steel out of alignment?
Right, because it's in a bolted metal box.
Yeah, it's bolted down.
Well, we have to stop thinking of the e-axle as a rigid, unmoving block of metal. It's a dynamic, flexible system.
Okay.
The manual points to 3 systemic stressors that conspire to force that tilt, and the first is entirely thermodynamic, thermal deformation.
Heat. Because electric motors make a lot of heat.
They do. And this introduces a clash of materials. To keep EVs light for better battery range, the outer housing is cast aluminum.
Which dissipates heat well.
Right. But the bearing itself has to be high-strength steel to survive those gigapascals of force.
And here's the fatal flaw the manual points out. Aluminum has a coefficient of thermal expansion, a CTE, that's roughly twice that of steel.
Meaning it swells and expands twice as fast and twice as much when heated.
So when you're driving hard, accelerating onto a highway, the oil gets up to, what, 120 degrees Celsius?
About 250 Fahrenheit, yeah.
And the aluminum housing just rapidly expands.
Normally, the bearing is held firmly by an interference fit. The hole in the aluminum is actually machined slightly smaller than the steel bearing.
So they have to press it in with a machine.
With immense force, yes. But at 120 degrees, that aluminum hole expands so much it completely loses its grip.
The interference fit drops to zero.
Zero.
Wait, so the housing is basically cooking in its own heat, expanding outward, and leaving the steel bearing rattling around inside like a loose tooth.
It is exactly like a loose tooth, and it gets worse because the housing doesn't expand perfectly into a larger circle.
Because of the shape.
Right, it has structural ribs, bolts, uneven heat from the inverter. So the perfectly round hole distorts into an oval.
Oh, man.
So now you have a rigid steel bearing and an asymmetrical expanding oval hole. The constraint keeping it parallel is just gone.
The moment torque hits, it's physically shoved out of alignment. We're building a precision instrument inside an oven that's actively changing its own shape.
It is terrifying, and that's just the first stressor.
Right, heat is just one. The second is mechanical. Shaft bending from gear meshing.
This is huge.
EV motors spin up to 20,000 RPM, and they use helical gears to multiply torque. And helical gears have angled teeth, unlike standard straight-cut gears.
The choice to use helical gears is tied directly to the EV experience. If you used straight-cut gears, they engage violently.
Like a race car transmission.
Exactly. They create a horrific high-pitched whine. In an EV, without engine noise to mask it, that whine would be unbearable.
So angled teeth slide into contact gradually. It's much quieter.
But physics demands a toll for that silence.
Right, because of the angle. When they transmit torque, they don't just push against each other rotationally, they create a wedge effect.
Huge radial separation forces, literally trying to push the two gears apart, and massive thrust forces pushing them sideways.
And those forces are so strong, the manual says they actually bend the solid steel output shaft.
They bend it elastically. The steel flexes under load and snaps back when you let off the accelerator.
But while you're accelerating, that thick steel shaft is physically bowing inside the housing.
And the bearing is mounted directly on that shaft. So when the shaft bends, the bearing tilts.
Goodbye parallelism. So let's stack this up. The aluminum is expanding, letting the bearing go loose.
Yep.
And at the exact same millisecond, the driver floors it, the gears act like wedges, the steel shafts physically bows, and the bearing is just actively shoved out of alignment.
A perfect storm of thermodynamics and mechanics. And it highlights a flaw in traditional engineering silos.
Like teams not talking to each other.
Exactly. You had a thermal team doing cooling and a mechanical team designing gears. But if they don't collaborate to model how thermal expansion aligns with mechanical deflection,
They missed the 1 milliradian disaster.
they have to simulate thermosolid coupling, understanding how heat compromises rigidity under load.
Which sets the stage for the third stressor, the offset architecture.
Right.
Many EVs use an offset layout with parallel shafts. They fold the drivetrain back on itself instead of a straight line to save space.
It's all about consumer demand for cabin space. By offsetting the shafts, the drive unit is compact, you get larger batteries and flat floors.
But it creates a severe mechanical imbalance, an asymmetrical load path.
Because the layout is folded, torque and heat aren't even. The bearing closest to the gears takes vastly higher loads.
Or cantilever load.
Think about holding a heavy bowling ball with your arm fully extended to your side.
That sounds exhausting.
Right, your shoulder joint takes all the strain. That shoulder is the gear side bearing. It's subjected to vastly accelerated dynamic misalignment.
It's pushed harder by gears, absorbs more heat, the aluminum expands more, the shaft bends more. It takes the brunt of everything.
And just to make it a complete nightmare, there's tolerance stacking during manufacturing.
Right, the system isn't mathematically perfect even on the assembly line.
If there's a coaxiality deviation of just over 0.05 millimeters when they machine the aluminum,
The bearing is practically born tilted. It enters the world halfway to catastrophe. Honestly, it's a miracle they survived the dealership parking lot.
it's a testament to modern metallurgy. But this brings up a fascinating question. When an e-axle does fail in the real world, how do they know what killed it?
Right, because a chewed-up bearing just looks like a chewed-up bearing.
Exactly. Was it heat? The bending shaft? Or something else?
The manual details this incredibly rigorous diagnostic framework to distinguish between mechanical fatigue, the crushing we just talked about, and electrical erosion.
Which is a completely different villain.
Here's where it gets really interesting. It is straight-up CSI for cars.
Diagnosing the root cause correctly is the most critical step. If you reinforce the steel shaft to stop the bending, but electricity was actually melting the metal.
Your stronger seal still fails.
Right. So the manual outlines a closed-loop, four-piece suite of forensic evidence.
Piece number 1 is morphology, the visual evidence. They put the damaged bearing under a scanning electron microscope. And S.
And electrical erosion leaves a very specific signature.
To the naked eye, it looks like a gray matte finish that turns into washboard-like fluting, like the grooves on a vinyl record.
Perfectly spaced apart. And under the SEM, they see microscopic craters and what's called a white layer.
A mechanical fatigue looks completely different.
Entirely different. Fatigue shows irregular, flake-like spalling. The metal physically tears away. The flakes often look like tiny arrows pointing in the rolling direction.
And Appendix B in the document even notes a color difference. Fatigue damage keeps its shiny metallic color.
While electrical erosion looks burnt, black, or flat gray.
So that's the visual fingerprint. But piece number 2, the oil and debris analysis. This is where the physics get truly bizarre.
It is wild.
You're telling me that in an EV, stray electricity is literally shooting through the grease, creating tiny lightning strikes that melt solid steel and turning that molten metal into microscopic snowballs.
That is quite literally what is happening. It's a phenomenal demonstration of high voltage physics.
How does that even happen?
It goes back to the EV's inverter. The inverter takes direct current from the battery and turns it into alternating current for the motor.
Using silicon carbide switches.
Right, turning power on and off thousands of times a second. This incredibly rapid switching creates high dVdt, a very high rate of change in voltage.
And this creates unintended side effects.
Exactly. It induces stray, high-frequency voltages onto the spinning metal shaft of the motor, and electricity always seeks ground.
The bearings connect the spinning shaft to the grounded outer housing.
So they look like a perfect bridge.
Yeah.
But there's a hurdle, the microscopic film of oil. Oil is a dielectric, it's an insulator.
So it doesn't conduct electricity.
Right, so the stray voltage builds up on the shaft trapped by the oil.
Until the pressure is so high it just punches through, like a spark plug firing.
That is the exact mechanism. When the voltage exceeds the dielectric breakdown threshold of that specific oil film, it arcs across the gap,
Microscopic lightning bolts.
striking the surface of the steel bearing thousands of times a second. The localized temperature of an electrical arc is thousands of degrees.
It instantly vaporizes the oil and mills a microscopic pit into the steel. Those are the craters under the microscope.
Exactly. And when that steel melts in a fraction of a millisecond, the physical rotation of the bearing flings the molten metal into the cooler oil.
And surface tension makes it form a perfect microscopic sphere before it cools.
Yes. So when forensic engineers drain the oil and filter the debris, if they see micron-sized spherical metal debris,
They have absolute proof that electrical arcing killed the bearing.
and the oil acts as a witness too. The extreme heat chemically destroys it. It turns pitch black, carbonizes, and smells burnt.
While fatigue debris is just flat flakes and the oil just looks oxidized.
Right.
It's absolutely proof.
Right.
But they don't stop there. Piece 3 is thermal geometry. They put the empty aluminum housing on a CMN, a coordinate measuring machine.
A very precise robotic probe.
It creates a flawless 3D map. If it shows perfect alignment at room temperature, but the bearing has that washboard fluting and melted debris.
It firmly points to electrical erosion. The geometry is sound, so electricity is the culprit.
But if the CMM detects the borehole deformed, or there's an ovality causing a tilt over 1 milliradian.
It points back to mechanical fatigue. The physical shape caused the failure.
In the final piece, piece 4, is the electrical path. They actively measure the invisible killer while the axle runs on a test bench,
Using a high-frequency oscilloscope.
sampling at over 200 megahertz, so 200 million readings a second, to catch transient voltage spikes higher than 3 volts.
3 volts sounds insignificant, but it's the exact threshold needed to break through that ultra-thin oil film and create the lightning strike.
Wow. So by capturing live data, correlating it with the CMM map, finding spherical debris and seeing craters, they close the loop. No guesswork.
They can tell the design teams definitively if they're fighting a mechanical issue or an electrical one.
Which is vital because the fixes are entirely
It's
different.
not different.
But as we dig deeper, we find that beyond electricity, there are 2 massive mechanical villains giving engineers nightmares.
Oh, yes.
And surprisingly, the first villain is the oil itself. Factor 1, lubrication and a thin oil film. Now, the EV industry is locked in a war over efficiency, right?
Where everything is about battery range.
So they use ultra-low viscosity oil. It's basically water compared to thick truck gear oil.
Because thick oil creates parasitic drag, the motor has to pull more amps just to churn through the fluid.
Which eats into driving range.
So they push for the thinnest oil chemically possible, but thermodynamics forces a dangerous tipping point.
Right. When the e-axle is under load and hits 120 degrees, this ultra-thin oil experiences shear thinning.
The molecular chains physically align and slide past each other too easily. The oil loses its structural integrity.
The pressurized liquid cushion collapses. And they measure this with the lambda ratio, right?
The lambda ratio is critical. It's the ratio of the oil film's thickness divided by the surface roughness of the two metal parts.
So if it's above 1.0, the oil is thick enough to keep the metals apart.
But if it drops to below 1.0, the oil is thinner than the microscopic peaks and valleys on the steel.
Because even polished steel isn't perfectly smooth. It has tiny jagged peaks, asperities.
Right. When lambda falls below 1.0, those microscopic peaks begin to physically crash into each other. Dry boundary friction.
They collide, weld together from friction heat, and violently tear apart as the bearing rolls.
It's called micropitting. It introduces stress fractures, which is the beginning of the end.
And high speeds fight the oil too. The manual mentions centrifugal starvation.
Up to 20,000 RPM. Centrifugal force literally flings the water-thin oil away from the center of the bearing where it's desperately needed.
It creates a localized drought.
Okay, I have to ask a seemingly obvious question. If the thin oil is causing boundary friction and destroying bearings, why not just use thicker oil?
I mean, that is the most logical engineering response.
Right. Just use oil that maintains a 2.0 lambda ratio at 120 degrees.
But it strikes at the terrifying irony of EV design. It's a high-stakes trade-off. Thicker oil absolutely solves the bearing problem. The components would last for decades. But that thicker oil creates internal drag, and the EV will lose a noticeable percentage of its advertised driving range.
It's weaponizing efficiency against durability.
Yeah.
Range sells EVs. If an engineer says we need thicker oil but we lose 15 miles of range, sales will kill the idea instantly.
Precisely. They are forced to walk an agonizing tightrope. The oil has to be just thick enough to barely prevent destruction, but thin enough to extract every meter of range. Operating on the ragged edge of physical destruction for efficiency, that's staggering.
It really is.
Okay, so that's the oil villain. The manual outlines a second mechanical villain, factor 7, thermal deformation, specifically thermal creep or the running ring.
This is a horrifying mechanism.
We talked about the aluminum housing losing its grip, but at 120 degrees, the outer ring of the steel bearing doesn't just sit loosely.
No, because of the violent rotational forces, the entire outer ring starts slipping and spinning inside the aluminum housing.
The running ring. And a bearing is designed so the outer ring stays perfectly stationary.
Completely locked in. When it spins, it's hardened steel aggressively grinding against softer aluminum. It destroys the borehole with fretting wear.
It's like the foundation of a house turning into a sinkhole. Once it slips, the whole house tilts and cracks.
The thermal creep excavates the aluminum. It destroys the geometric baseline. The bearing tilts, hits the 1 milliradian threshold, stress spikes to 2.5 gigapascals, and you get edge spalling.
The system cannibalizes itself. Okay, so we've mapped the battlefield. The heat cooks the aluminum, helical gears bend the shaft, the inverter shoots lightning through the grease, and the water-thin oil just flings away.
It sounds completely hopeless.
It really does. But Section 5 is the turnaround. It's how engineers fight back, outlining the 8D framework fixing the problem. So what is 8D?
8D stands for 8 Disciplines of Problem Solving. Developed by Ford in the 80s, it's the gold standard for catastrophic failures.
So it's highly structured.
Very. You move from immediate damage control to root cause analysis to permanent standardized design changes. The manual focuses on D3, D4, and D7.
Dive into D3. Interim containment. The emergency triage to stop the bleeding. You have thousands of cars on the road that are ticking time bombs. How do you fix a physical lubrication problem on sold cars?
Amazingly, they use over-the-air, or OTA, software updates. They beam a patch via cellular network that alters the electric motor's behavior.
That's incredibly clever.
It's a stopgap. The root cause of the oil thinning is excessive heat from continuous power. They can't physically change the oil in thousands of cars overnight.
So the software update just stops the driver from generating that heat.
Exactly. It implements stricter thermal throttling. It monitors temperatures and aggressively caps torque to ensure the oil never exceeds 100 degrees Celsius.
So by electronically keeping the oil cooler, it stays chemically thicker, the lambda ratio stays safe, and the asperities don't collide.
Right. The car might be slightly slower up a hill, but the axle won't explode.
The manual also lists physical D3 steps for cars coming in for service, shortening the first oil change interval to keep extreme pressure additives fresh.
Those additives act as a chemical backup when the fluid film fails, but they degrade. They also freeze inventory of new, lower viscosity oils.
But the containment strategy for thermal creep, the bearing spinning in the housing, is even crazier. How do you find cars where the bearing is slipping but hasn't shattered yet?
Acoustic forensics. They issue service bulletins for high-risk batches, but they don't tear the axle apart. They run NVH tests: noise, vibration, and harshness.
They attach highly sensitive diagnostic microphones to the axle housing while running it on a lift.
Because every mechanical component generates a distinct acoustic signature. When a bearing tilts by 1 milliradian or grinds against aluminum, it alters the vibration harmonics.
It makes a specific high-frequency vibration.
The NVH software can detect the acoustic signature of a deformed bearing long before the driver feels a shudder. They are literally listening for geometric stress concentration.
Like a cardiologist using an advanced stethoscope to hear a murmur before a heart attack, if they hear the spike, they replace the drive unit before it fails.
Exactly. So that contains the bleeding. Then they move to D4, root cause analysis.
And they're surprisingly honest here. They realize their original testing was deeply flawed. They only tested the structural integrity statically at room temperature.
Bolted to a hydraulic rig in a comfortable 72-degree lab. And this is where legacy automotive engineering falls short in the EV era.
A room temperature test completely misses the dynamic, multi-physics reality.
They completely missed the thermosolid coupling deformation. They didn't account for how much weaker the cast aluminum gets when soaking in 120-degree oil.
Or the viscosity decay of the ultra-thin oil under stress. They engineered a system for a rigid, cool world and forced it into a flexible, boiling, high-voltage world.
Which brings us to the ultimate solution, D7, standardization and preventing recurrence. How do they fundamentally redesign the system?
So what does this all mean for the actual design? I found this part profound. They introduced logarithmic crowning.
It's a brilliant engineering pivot.
We established a needle bearing is a flat, straight steel cylinder, but they realized they can't stop the aluminum from expanding, and they can't entirely stop the steel shaft from bending.
Physics dictates they will deform.
So instead of adding 50 pounds of steel to make it stiffer, they changed the microscopic shape of the bearing itself. They manufacture a microscopic a logarithmic profile into the roller.
It's a shift from rigidly overpowering nature to intelligently accommodating it. If the roller is perfectly flat, the moment the shaft bends, the sharp 90-degree edge digs in, causing that 2.5 gigapascal spike.
But with logarithmic crowning, the roller is ever so slightly barrel-shaped. It tapers away at the edges on a precise mathematical curve.
It spreads the load.
It's like a ship's hull. If a ship was a perfect rectangle with sharp corners, ocean waves would concentrate on the corners and shatter it. A curved hull lets energy roll across.
When the steel shaft bends, the barrel-shaped bearing doesn't dig its heels in. It allows the load to roll smoothly across its belly.
The load shifts, but with no sharp edge, the pressure never spikes to 2.5 gigapascals. And they simultaneously mandate maintaining a lambda ratio above 1.5 in all future designs.
Exactly. It spreads the load safely. But D7 is also about standardizing manufacturing. The manual mandates VDA 19.1 cleanliness standards.
Cleanroom level controls. Microscopic limits on airborne dust, because a single grain of hard dust in a 1.5 lambda oil film can initiate micropitting.
And they connect the robotic servo presses to the central network to monitor the exact physical force used to press every bearing into the housing, ensuring it isn't deformed during assembly.
They also upgrade the metallurgy to the CQI-9 heat treatment standard, dictating the precise thermal ramping and quenching process.
Converting austenite to martensite uniformly for maximum fatigue resistance.
And all this goes into a PFMEA, a process failure mode effects analysis.
The holy grail of reliability engineering. Translating theoretical physics into factory floor reality. They put these rules on the drawings using GD&T, geometric dimensioning and tolerancing.
They become critical characteristics, legally requiring suppliers to use statistical process control. If a batch deviates by a fraction of a millimeter, the line stops.
And to stop the electrical lightning strikes, they update the electrical architecture, adding grounding guidelines like carbon brushes on the rotor shaft, giving stray voltage a safe path to ground.
So it bypasses the oil film.
Exactly. If we connect this to the bigger picture, D7 standardization is the true Great Wall of reliability. Slapping in a thicker bearing is a band-aid.
Generational reliability means updating the corporate DNA.
Forcing electrical, thermal, and mechanical teams out of their silos to simulate loads together in a multi-physics environment.
The PFMEA matrix ensures these expensive lessons are institutionalized. It's a complete paradigm shift. Okay, let's take a breath and recap this incredible journey.
We covered a lot of ground.
We started with a microscopic 1 milliradian tilt. We discovered how thermodynamic heat expanding aluminum, mechanical wedge forces bending steel shafts, and cantilever loads all violently twist these bearings.
And the forensic toolkit inverters shooting miniature lightning bolts, leaving spherical debris.
We saw the agonizing trade-off with ultra-thin oil walking the edge between efficiency and destruction, and how engineers fight back with OTA updates, acoustic forensics, and fundamentally altering the mathematical curve of the metal.
It highlights the extreme hidden complexity of the clean energy transition. The serene driving experience is a carefully orchestrated illusion masking a chaotic environment.
It really is.
And tracing this raises a final, somewhat provocative thought. For a century, mechanics was about controlling contained explosions in a heavy iron block. It was dirty and loud, but mechanically comprehensible.
Right, you could see how it worked.
But in the EV era, components are vastly lighter, rotational speeds are exponentially higher, tolerances are microscopic, and high voltage, high frequency electricity is actively influencing physical structures.
So where does that leave the mechanic?
Are we rapidly reaching a point where the automotive mechanic of the future won't just need a socket set, but a deep working knowledge of electrical chemistry, thermosolid coupling, and maybe even quantum physics just to understand a failing wheel bearing?
That is a staggering thought. You take your car to the shop for a rattle, and the mechanic pulls out a 200 megahertz oscilloscope and lectures you about dielectric breakdown thresholds. The garage becomes a laboratory.
It basically has to be.
Well, thank you so much for joining us on this deep dive into the hidden world of a manual on e-axle differential bearing, failure analysis, and prevention strategies.
It's been a blast.
Hopefully, we've helped you unpack the incredible multidisciplinary science inside these machines. The next time you're cruising in an EV, silently accelerating onto the highway, take just a second to think about the microscopic 1 milliradian war raging beneath your feet.
And the brilliant engineering keeping you gliding smoothly.
Keep learning, keep questioning, and we will see you on the next deep dive.